Good morning, friends and dear students. It gives me immense pleasure to be here again for my course, Flight Mechanics. This course belongs to the fourth semester of Aeronautical students from Institute of Aeronautical Engineering, Hyderabad, India. I am Dr. Yagya Dutta Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today I am going to discuss about effect of wind direction on aircraft performance. A small amount I have already covered in the previous lectures. Today I will go some more detail about this effect of wind direction. So these are the topics which I am going to take. These are the topics: effect of wind in aircraft performance, types of wind, that is headwind and tailwind. Then we will see the ground velocity. Then we will see the range equation with ground velocity, effect of head and tail wind in fuel consumption on propeller aircraft, effect of head and tail wind for jet aircraft, and the gliding flight. In the Mann Ki Baat session, I want to share something about wind condition. Basically, I have worked in Indian Navy for 20 years and I have seen many operations, flight operations on board ships, aircraft carriers, helicopters on board ships, and always whenever aircraft is taking off or the landing, ship is made in such a direction that always wind should be against. That is the headwind. That is called the headwind. So I will just explain here. So this is the aircraft. In this aircraft, from this is fuselage. These are the wings. Here we have the delta wing. This is the fin or vertical tail. This is the horizontal tail. In wing, we have here at the tip, we have at the trailing edge of the tip, we have the ailerons, both the side. These ailerons will move in opposite direction. The wing which is going up, that aileron will move down because it has to produce more lift. And the wing which is supposed to go down, that will go up because that wing has to produce less lift. I think it is clear. So if I want to roll like this, means right wing is down like this, I have to produce more lift in this wing. So in this wing, I have to put my aileron down like this. So due to this down, there will be flow will be downwards and force will act upward. So a local camber is increased by putting the flap down here. But if you see here, this will be upward like this. So flow will go upward, a force will act downward. So this will go down and this will make up. So a net effect will be moving this thing with respect to the longitudinal axis. The axis which is from here to here, that is called the longitudinal axis. And if this force is higher here, this force is this side, aircraft will move like this. So this is the action of the ailerons. Ailerons are moving in opposite direction. That is the things. So and the wing which is going up, that wing will, the aileron of that wing will go down. So if you want to make pitching up, so it is with respect to the lateral axis, and this lateral axis is from wingtip to wingtip. So your aircraft, if you want to move like this, we need one control, that is called the ailerons. That is called the elevator. Elevators are always fixed in the horizontal tail at the trailing edge here. They will go up or the down. So if you want to make nose up, your you need a force which is pulling downwards. So we have to make up. Your elevator should be up. So the force will be downward. So it will go up. If you want the down, your elevator has to go down. So force will be upward. So this pitching moment will be done like this. If you want to roll, there is a rudder. If you want to roll towards the right, rudder should go right, because a force has to be generated towards this. So this will left. So it will move like this, because it is with respect to the center of gravity. So it will move like this. So in this way, all the three motions are performed on the aircraft. And again, I will just discuss about the headwind and the tailwind. If the aircraft is moving in this direction and wind is opposite to this, it is a headwind. And if the wind is towards from the tail or in the same direction in which aircraft is moving, that is called the tailwind. For the maximum range, we need the tailwind. But for landing and the takeoff, we need the headwind. So, because we need more lift that time during the landing and takeoff. So, this is a brief introduction on this, and this is my Mann Ki Baat of the day. So, effect of wind. So, here during flight, two kinds of wind encountered by the aircraft. First is the headwind and the tailwind. So, just I will explain here again, or I will take the aircraft. So, if aircraft is moving in this direction, I will put the different color. If your aircraft is in this direction and your natural wind is in this direction, this is called headwind. And if your aircraft is in this direction and your wind is in this direction, this is called the tailwind. And this is the headwind. So this is the difference between the headwind and the tailwind. Due to these winds, the relative velocity will be different in each case. So if you see in which case you have the more relative velocity, if you have the headwind, the relative velocity is more. So due to these winds, the relative velocity will be different in each case. When aircraft encountered headwind, head or the tailwind, then the velocity of the aircraft relative to the ground, that is called Vg, is different from the velocity of the aircraft relative to the free stream velocity, that is called V infinity. So ground speed will be different with respect to the free stream velocity. It should be kept in mind that aerodynamics of the aircraft depends upon the free stream velocity. Not the ground velocity. So your development of the drag, development of the forces, lift and the drag, these all are depend upon the free stream velocity, not the ground velocity. So all the calculation which we do, how to generate the lift and the drag and other forces, we are always considering the free stream velocity, that is the V infinity. So now we will see what is the ground velocity and how it is depend on your free stream velocity. There is a relationship between the ground velocity Vg and the V infinity as given in this diagram. So this you can see here, that if you are flying the aircraft in this direction and it is called V headwind. So, and here if you see, your aircraft is in this direction and your flow is also from this direction from behind, and this is your wind is from nose. This is the headwind. I will write H-wind, HW. So what is the relation between G and the V infinity? So in this case, whenever the headwind is there, the Vg is equal to V infinity minus VHW. So the ground velocity will be less than the your free stream velocity. And how much less? It is a difference of free stream velocity minus headwind. But if you see in this case, your ground velocity is high. If the tailwind is there like this, your ground velocity will be much higher, because in this tailwind velocity is added. So V infinity plus V tailwind, and here V infinity minus V headwind. For headwind, Vg is equal to V infinity minus VHW, and for tailwind it is V infinity plus V tailwind. So here if you see, Vg is high if it is from tailwind direction is there. Since the endurance of the aircraft depends on the aircraft relative velocity V infinity, so it is irrelevant to consider the distance covered over the ground for the calculation of the maximum endurance. So for the endurance, this is not effective, because it is not matter. The range is affected by the direction of the wind. But for the range, it's depend on the type of wind, that is headwind or the tailwind, encountered by the aircraft during flight. So for example, we can see that relative velocity of aircraft is 50 kilometers per hour, and the headwind is 50 kilometers per hour. So now your ground velocity will be 0, because 50 minus 50 is equal to 0. It means it is not traveling any distance. So the range will be 0. So for the range, your headwind is not good, but for tailwind is good. If in place of this 50 headwind, if you make the 50 tailwind, your ground speed will be 50 plus 50 is equal to 100. So now so this we can see, if it is tailwind, so now this Vg will be 50 plus 50 is equal to 100 kilometers per hour. But if it is in the opposite direction, it is hover. Your aircraft look like it is stationary in the ground. Your velocity will be, your range will be 0. Now we will find out the range equation, and from the range equation we will see what is the effect of the headwind and the tailwind. With above discussion, ranges depend on the ground speed Vg. So ground speeds need to be considered for the distance traveled over the ground just before takeoff and the landing. For distance covered S, we have the equation of Vg is equal to ds by dt, or we can write that this ds is equal to Vg into dt. And we already know the range equation, and this range equation R is equal to now Vg divided by Ct into L by D into ln W0 by W1, which we have already derived long back. These are the two equations which will be used for explanation of effect of the wind direction on the range. So if we talk about the fuel consumption on this, so above equation tells that range depends on the Vg. Vg is ground velocity. Weight of the fuel consumption, weight of the fuel consumed, percent distance covered over the ground. So per unit distance covered over the ground. So here weight of the fuel consumes divided by per mile is equal to specific fuel consumption horsepower of the propeller divided by efficiency of the propeller into Vg. So here Vg is important for the fuel consumption also. This fuel consumed, which also corresponds to the maximum range, will be the minimum if the ratio of HPR by VG is minimum. So the ratio of HPR by VG is minimum. So fuel consumption will be maximum. This term, if it is minimum, your fuel consumption will be minimum. Now let us discuss with help of the graph as given in the next slide. So if you want to decrease the fuel consumption, VG should be increased. So now we will see here. Let's draw a tangent from origin here. Here it is a power curve. Red color, it is a power curve. And if we draw the tangent from the origin, it will touch here. If we draw from here, it will touch here. So here we have the best range V infinity. This is the without headwind. Best range V infinity with no wind. Best range V infinity with no wind. Okay, so let's draw a tangent from O origin in HPR curve. This line intersects at point 1 and the 2. Point 1 is corresponds to the airspeed at which range is maximum without considering the wind effect. So in this case, without, if there is no wind, point 1 is the correct one. And point 2 corresponds to the airspeed at which range is maximum with the consideration of the headwind. So if the headwind is there, this is the point with headwind, this is the point 2. That is the with the consideration of headwind effect. Now what will happen with tailwind as given in the next slide. So if you see here, this is the your, if you draw this line from here to here, and this is here your headwind. So this much only your, and but here from here your VG is counted, not from here. Okay, so okay, we'll see here in the, if it is the tailwind, so what will happen? It is 0 and this is the minus and this is the plus. So tailwind is counted from here. Now it will start very near before the 1. So now the value of airspeed for maximum range with tailwind effects can be shown by the point 3 here. Point 3 is left intersection of the tangent and the curve for jet propelled aircraft. The percentage of the fuel consumption per mile covered over the ground, that is pound of the fuel consumed per mile, is equal to TSFC TR by VG. So if you see here, the VG is higher here because VG is counted from here. This is the VG, and if in the previous case it was only this much VG in the headwind. So here it is added, and your, if you see at 1, best range speed V infinity with no wind, best range speed V infinity with tailwind. This is the condition. So it is further VG is increased. So if the VG is increased, it is at the denominator. So your net fuel consumption of the aircraft will be reduced, range will be increased. So that is the benefit of this. So effect of headwind and tailwind for the jet aircraft. So propeller aircraft we have seen. Now we will see for the jet aircraft and how it is happening. So for the jet aircraft, pound of fuel consumed per mile is equal to thrust specific fuel consumption divided by Vg. So minimum amount of fuel consumed of per mile, which corresponds to the maximum ranges obtained with TR by Vg is minimum. So this term here, TR by Vg. So this should be minimum, and this will be minimum when Vg is maximum. So if you see here the Vg, so slope of the tangent lines are in the minimum value of TR by Vg. So these all slopes are the minimum value. Point 2 and the point 3 corresponds to the value of V infinity for best range for headwind and the tailwind. So this is the best range if we are flying in this, and this is the V tail and this is the V head. So here the fuel consumption, because Vg for headwind is low, and Vg for tailwind is high. So TR by Vg, if this is the high, this will be the low. So your specific fuel consumption of your aircraft will be reduced. If Vg is high, for the tailwind condition, Vg is high as shown here. This is the Vg from here to here, and for here from here to here, this is the Vg. So this much difference is added on the tailwind, and which gives the better fuel consumption properties. Now a small problem is given here. Which of the following is favorable for an airplane operation? That is the tailwind in cruise and headwind in landing. Tailwind both in cruise and the landing. Headwind both in cruise and the landing. Headwind in cruise and tailwind in landing. So just we will see that how it is happening. So which of the following is favorable for an airplane? So just now we have seen that if the airplane is here, so the first case, A, headwind in cruise and headwind in tail. So if it is a headwind, we have discussed that for the cruise, the Vg will be reduced, because if it is headwind, the net velocity Vg will be reduced. So V infinity minus headwind. So your net velocity is reduced. So it is not good for the cruise. So wherever the headwind is there, so tailwind in the, so headwind in both. So this is not correct. This is not correct. By this explanation. Now we will discuss the tailwind both in cruise and the landing. So now I will discuss the tailwind. So now if it is a tailwind here, tailwind is very good for range operation. So it is good. Tailwind is good for the cruise. So tailwind in cruise, so this is the one, and headwind in the landing. Tailwind in both in cruise and the landing. So this is not correct. This is the correct. Tailwind in cruise, and during the landing we want the headwind. So this is the your for the landing. Headwind, it gives more lift coefficient, more drag also. During the cruise, we want more distance, Vg should be high. So tailwind is good for landing. So this is your correct answer A. Now we will discuss something about the glide. We have already covered, but again I am just revisiting this. So the glide means what? If your aircraft is flying and in a straight and the level cruise flight, you have to go from one destination to another destination, or in the same destination you are making a circuit, you have to come down to your original airport. So after certain height it has to come down, so it has to move like this. This is called the glide. Glide is also used for when your engine is failed, or during your practice, whenever you want that your aircraft, if your engine fails, how pilot will be handling the aircraft, that time also glide is required. So here if you see, this is the lift, this is the drag. Here we don't have the thrust. Due to the engine failure, no power is available and these aircrafts starts to glide. This phase of flight is also called the unpowered flight. The equation of motion for steady unaccelerated flight, this you can see here. One is in the direction of, this is the velocity v, and another is perpendicular to this. So if you see, the L is equal to W cos theta, that is the first one. Second one is D is equal to W sin theta. So here W and sin theta. This W sin theta gives the forward motion. So if you divide this 2 to 1, so D by L, W is cancelled. So sin theta by cos theta, it is equal to tan theta. So this tan theta is equal to 1 by L by D. So also this tan theta minimum, L by D should be maximum. So theta will be minimum when L by D maximum. So we want this theta should be minimum so that more range it can cover on for the safe landing. So from this diagram we can see here that this is here range and this is here altitude. So from this diagram, glide with theta glide angle, so tan theta is equal to this vertical divided by horizontal, h by r. We can find out the altitude and horizontal distance r by this relation. So if you want, if you know the theta and if you know the altitude, how much range it will go, you can find out by using r is equal to h by tan theta. So pilot can calculate that if my angle is this, my altitude is this, how much distance I can cover. If the value of this theta is low, your value of r will be high. In the next class, we will be discussing about turn performance, general discussion on maneuver performance, basic maneuver of aircraft, fundamentals of turning flight, load factor and the bank angle, maximum allowable load factor for the different types of aircraft. These are the references: Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIA 2. Any questions, you are welcome to ask to my email. My email is ydwivedhi@gmail.com. Okay, this is my email. Here we have to. Please do like and subscribe. If you feel anywhere some mistakes are there, please let me know. You can comment on the comment box. Till then, goodbye. Thank you very much for the joining. Be tuned for my next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.